right, we're going to continue our exploration of computational geometry. We're going to look at the convex hull problem, which I defined last time. You have a set of points, and your goal is to snap a rubber band around these points to identify the smallest convex shape that contains all of the points. And I'm not going to prove some of the obvious things about this, but basically the convex hull is convex because it is the intersection of all of the half spaces that contain all the points, and half spaces are convex and intersections of convex bodies are convex. You'll also notice that this polygon has vertices, and those vertices will have to be points in the point set, right? Because if this vertex of the polygon was not in the point set, then you could obviously shrink the convex hull further, right? So the convex hull is defined basically by a subset of points that are vertices of the convex hull. And depending on the application, you'll often want to give those points in clockwise or counterclockwise order so that you can walk around the convex hull for various applications. Okay. Now, especially if you want to, if you're going to walk around the points in on the hull in order, you are implicitly sorting. So there is an omega of n log n lower bound if you have endpoints on the, if you have endpoints that you're finding the convex hull of. Yes? And there's actually reduction from sorting real numbers to computing a convex hull. It's not a very complicated one, but you can make this as formal as you like. Okay? So the question is, can we achieve this n log n? Can we match this n log n lower bound? And I'm going to show you one of the multitude of algorithms for convex hull, which is going to demonstrate a really cool idea called randomized incremental constructions, which I put into the family of sampling algorithms, right? In general, we talk about how if you're going to sample, you're going to get this sort of representative set of items. It's going to tell you things about the set as a whole. The items that you sample are going to be typical in some way. The idea of a randomized incremental construction is to, if you're building an artifact, a data structure or something that is made up of elements, you can add the elements one at a time, right, to create an incremental structure, right? If you want to make a binary search tree, the obvious way to do it is to insert one item at a time into the binary search tree, right? And these incremental constructions can have bad runtimes in the worst case. But it turns out that if you randomize the order in which you add items, then you often get nice expected behavior because the items that you the item that you add last is not first is not an outlier sort of item. So, for example, if you insert items if you build a binary search tree by inserting items one at a time, bad things can happen, right? What can you end up with if you just insert items one at a time into a binary search tree? Yeah? Yeah, if you happen to insert them in order, then you get a line, right? And it takes you time n to search that binary search tree. But what if you insert items in random order? Yeah? Yeah, how balanced does it end up if you insert the items in random order? Yeah? Depth log n with high probability. In fact, if you think about it, inserting items into a tree, into a binary search tree in random order, you're implementing quicksort. Okay, right? You put the first item you put in is the root item. That's the pivot. And then you have these two sides, right? And so the analysis of quicksort shows you that actually you end up with a nicely balanced binary search tree as a result of randomized insertions. We are going to use the same idea to develop a convex hull algorithm, okay? Which is to say, we have a collection of endpoints. We want to find the convex hull. What we are going to do is insert points one at a time and update the convex hull at each step. Okay, so that changes the problem of constructing the convex hull into the problem of updating the convex hull when you do an insertion. Yes? So is there more than one convex hull? Yeah?
I don't remember exactly how you defined it, but you could also just have like a massive square that contains all the points.
But how did I define it? Yes? Yeah, I actually originally defined it as the smallest convex body containing the points. So that implicitly says there's only one, because it's the smallest. Is it possible to have two equal-sized convex body that contain all the points? No, because yes, you can. Another definition, which you can show equivalent, is that it's the intersection of all the convex bodies that contain the points. So of course, there's only one that is the smallest. Okay, so yeah, and so I mean, I haven't given you the update mechanism yet, but it is going to be an update mechanism that can perform very poorly in the worst case. But we are going to show that if you insert in random order, then the updates are cheap, and therefore the convex hull algorithm is fast. Okay? We did make the problem easier. You know, now we only have to think about adding one point instead of computing the convex hull of all the points, but we also made it harder because we want this update to be efficient. So we kind of need a, we're going to use auxiliary, we're going to be doing these updates by maintaining a data structure that helps us do the updates efficiently, right? If all you had was the hull itself, it might be hard for you to figure out how to add the next point, right? If all I hang on to, right, I've done some inserting of points, and I have a current convex hull. Here's another point that needs to be added. What do I need to decide? Right? Yeah? So when you say which side I need to expand, do I always need to expand a side? Yeah, so the first thing I have to decide is whether it's inside or outside. Right? And if I'm lucky, the point I'm adding is inside the hull, and then I don't have to do anything. Right? But if I'm unlucky, if it's outside, then what do I need to do? Well, then I need to reshape the hull, right? And I need to figure out how to reshape the hull, right? What is going to need to be reshaped if I add a point outside of the hull? Well, we don't, pulling could have many definitions, so we need to be a little more formal. Yes? Exactly. It's kind of like a thing about sight lines, right? You kind of think about what this new point can see, and from the perspective of this new point, there's sort of is a farthest to the left and farthest to the right part of the polygon that it can see, right? And those limits are both going to be vertices of the polygon. And you basically need to swallow up a bunch of the convex hull, right? This point is, you're going to have to erase this chunk of the convex hull and replace it with these two new edges, right? So we're going to need to, I'll use the terminology you thought you said, sort of, we're going to erase some of the hull and replace it with two new edges I'll just call them the sort of extreme end edges or extreme vertices of the current hull with respect to the new point. Right? Now, if all we had was the current convex hull, this would be a kind of expensive calculation, right? Figure out where this point is in relation to the convex hull so that we can figure out if it's inside or outside and what are the sort of farthest vertices in angular position from the new point, right? So we are going to augment this evolving convex hull with some additional data that will make this update cheaper. So we're going to augment the hull that's in progress. What we're going to do is, first we are going to fix a point P0. I'll call it the origin, although it might not actually be the 0 coordinates, inside the convex hull. Okay. Let me make a new body. So we pick some point inside the convex hull. Okay. We're going to call this P0. Okay. And now, as we're going to create a series of point subsets. Or sorry, how do I want to say this? We're going to insert points P1 to Pn, creating sort of subsets so far, right? So after we have inserted point Pi, we'll have inserted a set of points that I'll call Si. And we are going to want to maintain the convex hull of Si as we add points until we get to Sn and have the convex hull of the whole thing, right? So what we are going to keep track of is for each Pi not yet added, we are going to track which edge of the convex hull of SI is crossed by the ray from P0 to PI. All right, so example, right, I have my PI, that's a bad example here. I have my PI over here, right? I'm going to keep track for each PI. I'm going to have this ray that runs from P0. And I'm going to have in my data structure that PI belongs to this edge. And I claim that this gives me helpful starting information for inserting PI into the convex hull. Right? So if we know nothing, the addition can be very expensive. As I said, you know, you'll have to walk around the entire convex hull to figure out where PI should be added and what needs to be changed. But if I have this edge, I claim that's useful starting information. How come? If you know this edge, what kinds of things can you decide quickly? Yeah? Good. So if I need to add the new point, I'm definitely going to have to delete this edge, right? But actually, this can also tell me whether I need to add the new point, right? How do I decide using this? How do I quickly decide from this information whether the new point needs to be added? Yes? Exactly, right? So to add PI, well, to decide if the convex hull changes, check if the ray hits the edge that PI owns before it hits PI, right? That's telling you whether PI is inside or outside of the convex hull, right? Oh, I forgot something. Is it easy to, I do need a P0. Can anybody suggest an easy way to build a P0? Yeah? Exactly. Exactly, right? So if I take 3 points, their convex hull is inside the convex hull of the whole body, of everything. So anything inside the convex hull of the 3 points is also inside the whole convex hull. And so I can just take the centroid of those 3 points. I can also, I think, take the centroid of all the points, but that's more expensive, so why bother? Okay. This tells us whether or not the vertex is outside the convex hull. If it's not, we're happy. If it is outside the convex hull, then we have to do some work. But this tells us where to start doing the work, because certainly this edge is going to have to be removed, right? Now how do I continue the work? Well, I have to remove the edge that belongs with that PI belongs to. What else do I have to do? Yeah. Exactly. I can continue to the left and right, removing edges until I'm done, right? It was clear in that picture, right, that what I have to remove from the convex hull is a contiguous set of lines, right? And how do I know when to stop? Yeah? Once P is on the other side of the edge. I think PI is already on, well, maybe that makes it. Oh, I see what you're saying. So I remove this because PI is outside it. I remove this because PI is outside of it. But I don't remove this because PI is inside of it, right? Yeah, I think that's correct. I just think of it in terms of sort of directions, right? That you sort of, if I think about the direction I'm moving, right? If I project this onto PI's sight line, right? For a while, things will be moving outwards, and that's what I have to remove, and then suddenly things start moving inwards. And that's just a projection calculation. So I think it's the same thing as what you were just saying, but just a different intuition. So what you can see is that it's very straightforward to implement this process of walking out along edges to find the extreme point on the left and the extreme point on the right. And once you have done so, then you draw your replacement lines. And so thanks to the fact that we had that this ray gave us a starting point, right? The work is proportional to the number of convex hull edges removed. That's a lie, though. That's what it seems to be. But I've actually, because of the way I've designed this data structure, I have some more work to do. Right? Like, yes, I have to update the convex hull in this incremental fashion, but what else do I have to do? I created this data structure that helps me with the updating of the hull, but that means I have to keep the data structure up to date. So what do I have to update as well as the edges of the hull itself? Yeah? What do I have to update about the edges that are being removed? I mean, I do have to remove them, but that's what I meant about updating the hull itself. But what else do I have to update? Yeah? Exactly, right? There's more update work, right? If PJ's ray crosses a removed edge, we have to give PJ its new edge. Or give the edge to, give PJ to the edge, or give the edge to PJ. We're going to use bidirectional pointers here, so we're maintaining the relationship in both directions. Okay, so this is work I've put onto myself that didn't exist in the original problem, because I don't actually need the data structure, I just need the convex hull. But I need this data structure so that the convex hull updating is cheap, and so I have to take responsibility for maintaining this auxiliary data as well. Okay? So we are going to analyze these two pieces of work. There's the work of updating the hull, and there's the work of updating the auxiliary data structure. Okay? Let's talk first about the work of updating the hull. Okay? Now, I already told you that this is equal to the number of edges removed in a given step, right? Plus, of course, I'm adding 2 edges, right? So I have to count that work as well. All right. Now, this is a little bit worrisome, because there's no real bound on the number of edges I might have to remove in a single step, right? The current convex hull might be this, beautiful, essentially half circle, right? And I add this point, and all of a sudden I have to remove all but 2 of the edges from the temporary convex hull. So a single insertion could be very expensive. Okay? But remember that I don't care about the individual operations. The question is, what is the cost over the entire evolution of the convex hull? Well, I just said that the cost in one step is the number of edges removed in that step. So the total cost is equal to the total number of edges removed over all steps of the data structure plus 2n, right? So if I could just get a handle on the total number of edges that are removed over the entire execution of the algorithm, maybe it would be a nice number. Any thoughts? Well, if an edge gets removed, what had to happen first? Yeah? Okay. Yes. It had to be added, right? You can't remove an edge that isn't added, right? So the total number of edges removed is at most the total number of edges added. Right? What's the total number of edges added? Well, how many edges do I add in a single step? Yeah? Exactly. Right? We just add those two outer edges, right? So we only add two edges for a given point. So this is at most 2n, right? So the total maintenance work is linear. Not a big deal, right? This, by the way, is the same argument as we made about last year's convex hull algorithm, if you were in advanced algorithms, okay? The work of adding and deleting edges is actually quite small. It's the rest of the work that's expensive. I mean, I said this one way, but you can also just say that you're going to be that what we're doing is we're charging the deletions against the insertions, right? When we insert an edge, we give it an extra unit of work credit for the ultimate deletion of the edge. And so the deletions, that makes the deletions free in an amortized analysis. So the only thing that we have to worry about is the data structure maintenance. And what's the worry here? What on the surface of things could go very wrong? Yeah?
Like on a single insertion, you could like update like a lot of points, but if you only like affected a few edges.
Exactly. If all of the points that I haven't added yet are here, so they're all owned by the same edge, then when I update the convex hull, I'm going to have to update the data structure for every one of those points, right? But what does randomization say if there are lots and lots of these points here? Right? Same intuitions as we've been going with all along, right? We were looking at arrangements of lines. We said if there's a triangle with lots of lines through it, then probably we picked one of the lines in it, so it's not there, right? Well, similarly here, if there's tons of points here, then probably we picked one of them already, and this edge is not here, right? But there's a very elegant analysis for evaluating this through when you're doing a randomized incremental construction, which is called backwards analysis. So analyzing this forward, it's complicated and messy and worrisome, right? We're not sure what state we're in, and so we worry that there are tons and tons of points that need to be updated as we add. It turns out to be much easier to analyze if you imagine running the algorithm backwards. Okay, and we will see this very quickly. Right? So the algorithm, as defined, says add a vertex, remove edges, and update edge pointers. We are going to run all of this backwards. So we're going to start with everything added and with all of the edge pointers at their final locations. We are now going to pick a random point to remove from the set, and we are going to unupdate the data structure, right? If we remove a point, right, what can happen? Well, it might be a point that is inside the hull, in which case we don't have to change anything, right? But if we remove a point that is on the hull, we have to unupdate the ray pointers, right? So here's my hull. Right, we're doing backwards analysis. So we may have already removed a bunch of points, okay? But we've only, they haven't vanished. They're still in our problem. And so as we're doing our backwards analysis, these points that we've removed still have their ray pointers, right? But points that we haven't removed also have ray pointers, yes? And when we now, take some point and remove it, we undo what we did, right? We take away the two edges that belong to this point that's on the hull, and we replace possibly a lot of new edges that join the smaller convex hull. Yes? So we're going to remove the points from the hull one at a time, and we are going to unupdate all n ray pointers. And this is including for previously removed points. And this is just going to turn out to be easier to analyze. This is clearly exactly the same work, right? We're literally running the algorithm backwards. So the number of steps that it takes is going to be exactly the same. Okay. So when we do this backward analysis, let's talk about the expected number of ray updates when you remove P sub I. Remember, we added P1, P2 up to Pn. We're removing Pn down to Pi, right? Down to P1. So what can we say about the expected number of ray updates that we need to do when we remove a point? Well, let's see. If Pi is not on the current hull, we're going to remove 0. We're going to do 0 ray updates, right? If it is, what rays are we going to have to update? Yeah? Exactly. If Pi is on the hull, we have to update the rays through the two edges belonging to Pi. Yes? All right. From that perspective, right, what is the probability that I have to update a particular ray? Yeah? Why? Exactly, right? I have to update this ray if I remove its edge, right? I remove its edge only if I remove one of the two vertices that are at the ends of its edge, right? Okay. But there's only two of those. I am picking a random, right? This is, I inserted in random order. So I'm removing in random order, right? So I am choosing a random one of I vertices to remove uniformly at random. And so that gives me this probability 2 over I when I remove the ith point, when I remove pi. Yes? So the number of updates, the expected number of updates for pi is just 2n over I. Right? Because there are n rays, and each of them has a 2 over I chance of being updated. So now we're done, right? Now the total number of ray updates over all n steps is what? Yeah? Exactly. Total updates over n phases. Hang on, let me write it first and then you can disagree. Is 2n sum of 1 over I, which is 2n h sub n, which is order of n log n. Okay, what is your concern? No. I is not the size of the current convex hull, and that is very important. We are not choosing a random vertex on the hull to remove. We are choosing a random unremoved vertex to remove. Sorry, the ambiguity is, what does remove mean, right? So remember what we were talking about in this algorithm is we are adding points to our set. We're going from S1 to S2 to S3 to S4, right? So we've got this nesting of sets. And each time we add a point to the set to our set, it might change the convex hull or it might not change the convex hull, right? So in this backward analysis, what we are doing in each step is removing a point from our set. We're going from SI down to SI minus 1. And SI is not only the points of the hull, it is the points that got added first or are getting removed last. And so SI has I of those points, and we don't know how many vertices are on the convex hull at that point. Okay? Yes? Exactly, right? The 2 over I here is saying, like, if you were going to choose a random vertex to remove from the hull, then it wouldn't be I here. It would be the number of vertices currently on the hull, about which we have no idea at all. But it's going to be smaller than I because there's only I points left. So it's better to use I. And so you see how simple and elegant this backwards analysis is, right? Because we know that whatever is going on with the hull as a whole, there are only two edges associated with a particular vertex that we are removing or uninserting. Okay, so backwards analysis shows up a lot in computational geometry. This is just a particularly simple and elegant demonstration of it. Okay, if you have the Motwani-Raghavan book, there are several other really interesting computational geometry problems. Again, for those of you who took advanced algorithms last year, we talked about Voronoi diagrams, which are this fascinating geometric data structure. It turns out there's a beautiful randomized incremental construction for Voronoi diagrams that has the optimum order on n log n runtime. And there's also something called trapezoidal decompositions, which are another sort of point location data structure, and those also have a beautiful randomized incremental construction. So well worth knowing about. Okay. So I said that convex hull is just like sorting. So now we're going to sort of wrap up the story of convex hull in that it has gazillions of algorithms, n log n lower bound, so on and so forth. But it's not quite the same as sorting because you don't have to ask for the points on the hull to be in order, right? You can say, I'm just going to settle for knowing which points are on the hull without knowing more. Actually, no, sorry. Even with the order, there is a sense in which you don't need to know everything because you're only interested in the points on the hull. So, unlike sorting, convex hull also has a collection of output-sensitive algorithms. And you can achieve a running time of n log k if there are k points on the hull. Okay, so if there is a triangle, if the convex hull is a triangle, then it's linear time to construct it. And there are both deterministic and randomized algorithms for this. The output-sensitive randomized algorithm does not use a randomized incremental construction. It's actually a lot like quicksort. Only you sort of quicksort on angles around the convex hull instead of quicksorting linearly. Okay. Convex hull does have generalizations to higher dimensions, and randomized incremental constructions work for higher dimensional convex hull as well. So there's a lot more richness that I don't have time to show you. But for example, this is somewhat surprising. It turns out that you can do the 3D convex hull in order n log n time. Okay. Once you study computational geometry, you tend to assume that the cost goes up with dimension, and it would be n squared in 3D, but it's not. It's still n log n. Then it goes up. Yes. No, I believe, if I remember correctly, it is actually n to the floor of d over 2, and I have no idea why. Yeah? We showed expected time. So what's the natural follow-on question? Yeah? Is it with high probability? I guess by next week, you'll know the answer to that question. Okay? Yes? I don't think, I believe that the reduction from one to the other kind of forces the points to get output in sorted order, but I could be wrong, so I'm not going to say so with certainty. Okay. Other questions? All right, then let's take our break and get those brains cleared again, because we're going to now study a relatively sophisticated topic of linear programming. All right, so logistics first. I messed something up with the posting of the problem set, and it came a day late. Somebody asked whether I would extend the deadline. I think logistically it may actually make more sense for me to just grant everybody a couple of extra Slack points, because that way you can decide if you want to use them this week. I expect most people will still prefer to submit it on Wednesday, and that way we can start grading it on time. But I have to figure out the right number of Slack points, and I'll send an announcement about that. Also on the homework that was posted, you will notice an optional problem of submitting a project proposal. It's optional this week. It will become required next week or the week after, because I want to look at your project proposals and make sure that they are suitable for the class. There is a project handout, which either is or shortly will be on the website, so that you can see a description of the project. The general story I sketched out in the intro to the class. You have an option of doing a reading project where you just read a bunch of cool papers about randomized algorithms and write a sort of synopsis and summary of them. Or you can do a implementation project where you take some cool randomized algorithm and see how it performs in practice. This doesn't mean you just implement it. An implementation project requires an actual scientific evaluation of it, where you develop test data sets that are hard in interesting, meaningful ways, and study the performance and evaluate what heuristics might be used in order to improve performance in practice, and so on and so forth. So it's not just an implementation project. It has as much science as the others. And the last is a research project where these are my favorites, actually. If you happen to be working on something in computational biology or hardware design or something, and there's a problem that can be solved with a randomized algorithm, now's your chance to try and see if you're able to make some progress on it using the techniques that were presented in this class. Those tend to be the most creative. They're also the most open, because but at this, one challenge is whatever project you do, it has to be comprehensible to everybody in the class, not just to me. And that can be hard if you're working in a very esoteric area, because you need to explain enough of the background for anybody in the class to be able to follow what you're doing. Okay? So once you turn in your proposal, I will evaluate it and let you know if it seems suitable. And so there's a trade-off. The sooner you do that, the sooner you'll have confirmation that it's a good proposal and you can get started working on it. On the other hand, there are some really cool topics that we haven't covered yet. We're going to be studying randomized rounding, metric space embeddings, and Markov chains. And you might discover you want to do your project on those topics. So you might not want, you might want to wait. So that's why I put it as an optional, an option for this week. Are there any projects should be done in groups, just to make it more fun for everybody and reduce the number of projects that we actually need to look at. I will point, it is an elephant in the room that, read a bunch of papers and summarize them. There are some tools that are pretty good at that now, right? Don't use them. As I said at the beginning of this class, we're trying to develop some skills here, and I believe that those skills are extremely useful, even in the presence of these tools. And if you use the tools, you won't develop the skills. So take that responsibility on yourself. Any questions about the project before I go back to lecture? No? Yes? 3. It shouldn't be 4, because then it gets too distributed, and it can be 2 if there's an odd number or something like that, or if you can't find some third person who's interested in the project. It really shouldn't be 1. And I guess also logistics. After Thanksgiving, there will be no homework due, and you'll be able to work entirely on your projects. I also probably won't be lecturing. I might have an optional lecture or two, or we'll see. And then on Monday, 2 days before the last day of classes on Wednesday, we'll have a peer editing session where you will all bring in your projects and get feedback on them, which I have now many years of experience dramatically improves the quality of the projects to have somebody else look at them before I look at them or before the TAs look at them. And then they'll be due on Wednesday because that's the MIT rule. I can't make any deadlines after the last day of class. Okay. Yes? I have no idea. I just do N+1 every week. But the last one is, I'm not going to have you working on a piece set over Thanksgiving or after. So the last one will be due the Wednesday before Thanksgiving break. Okay. Which means that the last couple of lectures will be I mean, they'll be interesting, but there won't be any problem sets on them. So things will be pretty flexible. You won't need to be here on Wednesday before Thanksgiving if you don't want to be. Okay, although you miss a really cool lecture. All right, so linear programming. Who's seen linear programming before, at least defined? Yeah? Okay, good. So I'll whip through that part, right? So linear programming is the problem where you have a d-dimensional, d variables, and you have some set of n linear constraints, inequalities. And a linear objective function. And you want to optimize it subject to the constraints. And I spend a lot of time in advanced algorithms going into depth about linear programming as sort of an algebraic problem. We talk about it in matrix form. One of the things that I prove is that every linear program can be rewritten as a sort of canonical form linear program where you're trying to minimize something. Max. Where you're trying to maximize something under a set of linear inequalities, right? And we developed a number of algorithms for it. I talked about simplex, which was the first algorithm developed for linear programming by George Danzig during World War II. It was used for, logistics for troop supplies and things like that. And that really founded the field of operations research and optimization generally. There's the Danzig Prize now for operations research. And the simplex algorithm is, unfortunately, an exponential time algorithm. And this is a lower bound. The people have demonstrated, here is a polytope where the basic simplex algorithm does take exponential time. There are lots of heuristics that you can throw onto simplex, and if you throw in enough different heuristics, we're not sure if it's still exponential time or if somehow it becomes polynomial. But the next big breakthrough was the ellipsoid algorithm in '79. That was the first polynomial time algorithm. But it's weakly polynomial, for those who are familiar with that terminology. It depends on the number of bits. It's polynomial in the size of the input if you count the number of bits that are used to represent the numbers. Okay, so if you want to do linear programming at super high precision, it gets slow. And then there was another breakthrough on interior point methods, which are polytime and practical. And since then, linear programming has really become a sledgehammer for solving all sorts of really difficult optimization problems. And it's probably one of the most intensively studied optimization problems. Pretty much everything that we've talked about, like max flow and so forth, is just a special case of, and shortest paths, minimum spanning tree in a certain sense. They're all special cases of linear programming. The NP-hard problems we talked about, like independence set, are integer linear programs. So linear programming is very general. But all of this really digs into the algebra, right? We talk about the determinants of the matrices and the number of bits that are needed to represent them, and so on and so forth. A completely different way to think about linear programming is to think about it as a computational geometry problem. Right, I mean, like, the interior point methods are all about gradient descent and, calculus and numbers. But you can instead think about it in terms of geometry. Where each constraint is just a half space. And, of course, the vertices of your polytopes are just intersections of subsets of the constraints, right? Or, sorry, constraints are half planes, are planes, right? And so again, this uses a lot of stuff that we proved last year, but we know that the optimum of a linear program is going to occur at a vertex. And so in a sense, without talking at all about numbers, you can say that what I want to find is the optimum vertex of the polytope that is defined by these constraint planes. And that just means I want to find which subset of the constraints are the ones that define that optimum vertex, right? So finding the optimum is really just about finding the right subset of planes whose intersection is that optimum. And to keep things elegant, I'm going to assume general position, right? Which means that there are, we're in dimension D. There are no D+1 hyperplanes that all intersect at the same point, right? You can always transform a problem into general position by adding a small perturbation to each hyperplane without appreciably changing the problem, right? So if you're in general position, the optimum is D of these hyperplanes. And we just want to figure out which of the hyperplanes are the ones that define the optimum. And this just does away entirely with all of the algebra, all of the numerical stuff, and just lets you think purely about the structure of these hyperplanes. So have I sort of given you a good picture of how we're going to be thinking about linear programming for this class? If I have a set of hyperplanes H, I'm going to refer to this set of D hyperplanes as B of H, where B stands for basis. It's just the thing that is the base that constrains the optimum. I may also just forget and talk opt of H, although technically that is the value of the objective function at B of H. But hopefully there won't be any confusion there. Okay? So somewhere among these n hyperplanes, there is the right set of D of them, and we need to find it, right? This makes it a lot like the other combinatorial problems that we've thought about, right? Somewhere in this graph, there is the cheapest tree, and we need to find it. Somewhere in this graph, there is the cheapest cut, and we need to find it, right? It's all about finding the right subset. Just springing this on you with no preparation, any thoughts on what sort of algorithmic technique might be helpful here? Right? If you just, if your study of algorithms was just learning what we learned in this class, what sort of strategy might you want to consider for finding the optimum set of hyperplanes? Yeah? Yeah, what might we hope to learn from sampling a set of hyperplanes? Right? I mean, it's natural to think about recursively finding the optimum with that subset. What might it tell us? In what sense might we get an approximate solution if we look at sampling a subset of the hyperplanes? We're being very structural here. It's not about numbers, so we're not going to be talking in terms of how close is the value of this optimum to the value of the true optimum. But is there something we might be able to say structurally about how the optimum of this subset is not too different from the optimum, from the true optimum? Yeah? Fraction of tight constraints. So you're hoping that when we take this sample, we will get a bunch of the constraints from the optimum in the sample. And so we'll have sort of a good fraction of the optimum constraints. That's what you're saying? Okay. So if we take a small sample, how much of the optimum constraints are we going to have? Well, not a lot, because it's a small sample. Right? What else might we think about? What if you think about something like the MST? Right? MST and linear programming are actually more related than they seem at the surface, because they're both actually kind of a matroid optimization problem. They're both about independent sets. It's just that in graphs, it's the trees that are the independent sets. Yes? Good. So, if we think about a linear programming problem involving lots of hyperplanes, here's a nice 2D linear programming problem, right? I'll just assume that all of the hyperplanes are constrained upwards, and I want to minimize some objective, right? Gravity is my objective function. So just looking at the picture, you can sort of see that some of the hyperplanes are high and some of them are low. And it's the highest hyperplanes that define the optimum. And the low ones are just very far away from anything relevant to the optimum. So intuitively, if I pick a bunch of hyperplanes at random, right, what's that going to do for me? Yeah? Yeah, exactly. It's like if I take this subset and find the optimum of the subset, some of the hyperplanes are below that subset. They're kind of useless in some sense, right? Or they appear useless. Unfortunately, in high dimensions, it's not that straightforward, right? Like something may appear useless for this particular collection of hyperplanes that you're looking at, but it turns out if you're using different hyperplanes, it might turn useful again, because the other hyperplanes take you to a completely different place where that low hyperplane is now a higher hyperplane. But the intuition is there, right? So the idea that we're going to use is we're going to choose a random subset. Okay. And we are going to solve it, generally recursively. And then we are going to examine the violated constraints. And see what we can learn about the problem by looking at that. So this is, again, very much in line with what we did for minimum spanning tree, right? We sampled, we built this minimum spanning tree, and then we said which edges are actually improve on the solution that I have, right? Now, it would be really nice if, as with minimum spanning tree, all of B of H violated anything non-optimum. Unfortunately, that's not quite true. Okay. The violated constraints might not contain all of the basis hyperplanes. But, as I will quickly show you, it will contain some of B of H. So, solving a random subset tells you something about the optimum. And we are going to leverage that into an algorithm for finding the optimum. Okay. Now, why is this? Well, the opt of R is better with respect to the objective function than the opt of H, right? Why is that? Yeah? Exactly. We took a random subset. We threw away constraints. So it can't make the objective worse, right? But conversely, right, any point feasible for the basis of H can't be better than opt of H, because that's the definition of, or sorry, opt of H, because that's the definition, right? Opt of H is the best achievable point if you have the constraints in H, right? But B of H are the constraints that actually matter for H, and so the best achievable point is the opt of B of H and also the opt of H, and you can't be better than it. So if we have a point that is better, it must be violating one of the constraints B of H. Okay. So we're already on a promising path, right? If I choose a random subset of hyperplanes and recursively optimize it, and then I look for violating hyperplanes, one of the optimum hyperplanes will be in there, in that violating set. Okay? So what should I do now? Yeah? Good. So the violating constraints include a piece of the optimum. So what I can do is I can say, I'm going to make all of these, I'm going to permanently commit to these violated constraints, right? In my future random sample, I'm going to include all of these violated constraints and a few more random hyperplanes, right? And because I included those violated constraints, I also included this particular constraint from the basis of H. And so, of course, in this new sample, I'm not going to violate that constraint that I kept, right? Which means that the next time I do this, I'm going to have to end up violating, my new violators are going to contain a different constraint of the basis. Does that make sense? So essentially, you can imagine repeating this process, right? I have a current set of sort of active constraints that I have decided are important. I pick some more constraints at random. I optimize that combination. I get a point. I get an optimum point there. Now I look for violators of that point. And among those new violators, there is another constraint of the basis that was not yet active. Because if it were active, I wouldn't be violating it. Right? So if I repeat this, right? So add the violating constraints to an active set, which I'll call S, right? Next, choose a new random R from the non-active constraints and optimize over that, right? That is violated by a different constraint of B of H, right? And so I can take the next set of violators and add them to the active set, right? How often do I need to do this, right? Take my active set, take a new random addition, optimize, look for violators. That brings in a new part, a new constraint from the basis, right? How often do I have to do that? Yeah? Why? Exactly. After D iterations, all of B of H is contained in my active set. So the next optimization finds B of H. So that's the general plan. I should say, I'm going to be presenting several different linear programming algorithms to you in sort of chronological order of their development. But this is the first of the several. And we're going to be recycling several of the ideas. So that's our algorithm, which is called SAMP-LP. It has a set S of active hyperplanes. And now I'm going to throw in some magic parameters, which we will prove work well. If the number of constraints is less than 9D squared, then run a regular simplex algorithm. Here you should think of D as kind of a constant, right? And this takes D to the order D time. It's exponential in D, but who cares? Okay. Otherwise, you pick your random R contained in H minus S random of size D square root of n. Okay. And then you find X as a recursive optimization on R union S. You set V to be the hyperplanes that violate X. And then if V is less than or equal to 2 square root of n, you add V to S. And you repeat this until you have d successes of this step, at which point you will be done. Okay. So this is the formalization of the ideas that we discussed. Is it clear? Okay. Now, the key claim is that the expected number of violating hyperplanes, if you have chosen this many at random, is at most square root of n. And I'll prove that next time. But let's accept it for now, right? This is, again, intuition from minimum spanning tree, right? That not too many, if you pick a reasonably, the larger the set you pick, the fewer violations you're going to have in everything else. Also from the arrangement of lines intuition, right? So the expectation is less than square root of n, so the probability of this event is at least a half by Markov's inequality. So the number of times that you're going to need to do this is order d, right? You're going to do 2d rounds in expectation, right? Because we need d successes, and we have a 50-50 chance of success each time. Okay? So now if we fill in some details, the work that we have to do is mainly the computation of the violating hyperplanes. Right? We have a candidate x. We have to see which hyperplanes violate it. That takes order. Well, a hyperplane is just d numbers, right? We're basically need to compute dot products, right? So this takes order d squared n time. Actually, I think it should be dn, although it doesn't really matter in the. No, sorry. It's order dn to check per round. So order d squared n over my 2d rounds, right? Now, the other thing to notice is that each time we have a success, we add 2 root n violating hyperplanes, right, to our set. But we're only going to be doing d success. We're only going to do this for d successes. So in total, we're only going to be adding 2d root n hyperplanes, violating hyperplanes to our active set, right? D rounds of adding 2 root n violating constraints means that the size of S is going to be about 2d root n at the end, and all the time. So now we can write down a recursion, right? But just